Hess's law. So Hess's law is a way of measuring, so it's called the indirect method of measuring enthalpy. So delta H. So the heat that is associated with, well, more than heat, but primarily heat of a chemical reaction. Because enthalpy is a state function, whether you do a reaction in 1 step or 10 steps, what matters is the final condition of the products being made ultimately versus the energy or the enthalpy of the reactants that you had initially. And with all that, that's the principle behind it. Let's see what a Hess's law problem looks like in action. Okay. So here we have graphite reacting with oxygen gas to make carbon dioxide. And if this occurs in 1 step, if it did occur in 1 step, you would get an enthalpy of negative 393.5 kilojoules. It's an exothermic reaction, and that much energy would come out. It's 1 step. But what's illustrated here, what if the reaction occurred in 2 steps? So here we have graphite, just going to abbreviate it as carbon solid, plus oxygen gas, reacting to make carbon monoxide gas, and half a mole of oxygen. This equation. So here, the reactants, intermediate products, okay, energy is released. This enthalpy is exothermic. Okay, so 1 mole graphite reacting with 1 mole of oxygen gas to make 1 mole of carbon monoxide and half a mole of oxygen gas. Step 2. Here are products from the first reaction are the reactants for the second one. So carbon monoxide gas plus half a mole of oxygen gas react to make carbon dioxide. So, like a mathematical equation or spectator ions from earlier in your chemistry experience, carbon monoxide here is what chemists call an intermediate. It's produced in the chemical reaction or the series of reactions, but ultimately it's consumed in the reaction. So we can cross those out. Carbon monoxide is a reactant here, product here, they cancel, and then half a mole of oxygen will cancel. And those two reactions sum together to make our initial reaction. Carbon graphite, or solid graphite, reacting with oxygen gas to make CO2. one step, releasing negative 393.5 kilojoules of heat, or two steps. We added the two equations together, we can add the enthalpies together. You see that those two reactions will sum and give us the same enthalpy value, whether it occurs in one step or two steps. Two steps, negative 393.5 kilojoules. One step, negative 393.5 kilojoules. Why it matters? Often whenever you can have a chemical reaction that might be dangerous in one step, in a sense that it releases too much energy all at once. Okay. Because it could be a dangerous reaction that if you had, not this reaction in particular, but if you did have a reaction that released all of its energy in one step, that could cause issues, as opposed to if you can control a reaction doing it in a stepwise manner, you can make a reaction safer or more efficient, especially for biochemistry or biochemical reaction. So practice with Hess's law. So this is a typical Hess's law problem. You're asked to find an enthalpy value for a single equation, and you're given two independent equations with a known enthalpy value. So Hess's law problems, you're allowed to do two things. One is you're allowed to reverse or quote-unquote flip the reaction. Why would you do this? If we look at NOCl in the equation we're trying to find the enthalpy value for, here it's a reactant. If we go looking for it in our equations with known enthalpy values, the only place it occurs is here. Here it's a product, reactant, product. So you reverse or flip the reaction to get your chemicals to match. So you do this to match your chemicals. So products or reactants. The other thing you're allowed to do in Hess's law problems is multiply the chemical equations by factors. The reason I say factors is you don't always have to use whole numbers, but whole numbers are common. So for example, if we go back and look at NOCl, the final equation has 2 moles of NOCl as a reactant. Our only source of it has 1 mole of NOCl. So you do that to, again, match the number of moles that are desired. So those are the 2 rules that you're allowed to do when you're doing Hess's law problems. So given those rules, that bottom equation has to be flipped, reversed, and multiplied by 2. And what would that look like? So if I rewrite it down below, 2 moles of NaCl gas will react to make 2 moles nitric oxide gas and chlorine gas. And the enthalpy value, delta H, is going to have the sign changed. It's no longer going to be negative. NaCl went from being a product to a reactant. It's going to be doubled. So that's going to be 77.2 kilojoules. That's an example of applying both of those operations to the equation. 2 moles of NaCl as a reactant, 2 moles of NaCl as a reactant. So the next equation, we just continue moving on. N2, here is a product. The only equation where it's a source or that it occurs is here. We have half a mole of it and have it as a reactant. So we have to do the same operation. We have to flip this, or operations. You have to flip it and multiply by 2. So what that looks like, so we have 2 moles nitric oxide gas reacting to make 1 mole of nitrogen gas and 1 mole of oxygen gas. And what that does to the enthalpy, the sign's now negative, and it will become 180.6 kilojoules. And then to confirm everything, we cancel our intermediate. We've got nitric oxide here as a product, here as the reactant. Again, since those are intermediate, or nitric oxide is an intermediate, it's created during the course of this reaction, but it's ultimately consumed. If we write, we have 2 moles of NaCl gas decomposing to produce nitrogen gas, 1 mole of it, plus oxygen gas, plus chlorine gas. And this equation matches the equation that we're looking for the enthalpy value for. So the enthalpy of this reaction, if I do my math correctly, is minus 103.4 kilojoules. If you encounter a chemical that occurs in both equations, the general rule is you always start with something that only occurs in one equation. It's a guideline, if possible. Start balancing or changing the equations that are your only source for a chemical in the final question, or in the final equation you're asked to solve for.